All right. Yesterday we went through this. This was the proof of our cosine um, formula, sum and addition formulas, and we did the sum formula. I'm going to show you the difference formula here in a moment. But I made a slight technical error, not a huge thing. Still worked out the same way. But when I squared this right here, okay, it should be sine t squared, which I've got, 2 sine t sine s, but then this becomes sine squared of s, right? Okay. And I did the same. I'm an idiot. I did the same thing right here. This is cosine squared t minus 2 cosine t cosine s, but this last one then would be plus cosine squared s. So that should be an s, and that should be an s. They still evaluate to 1, right? Okay. So that doesn't change anything. Doesn't change the formula at the end that we ended up creating. So as you maybe look through your notes or whatever, look through that video again, note that typo is there, but it doesn't ultimately impact too much else. So yesterday we talked about that top one. That's the one I just showed you, and we just proved it. I want to show you how this bottom one stems directly from that pretty easily. Okay, that bottom one is going to be generated by the top one. So I'm going to take the top one and I'm going to write it as cosine of s plus t. Okay. Well, actually, I'm going to write this one. I'm going to start with the bottom. Let's do it this way. If I write the bottom one, cosine of s minus t, is that identical? What do we know the definition of subtraction to be? When you first learned in Algebra 1 what we call subtraction, what was the phrase that they used? It's adding the opposite, adding the negative version, right? So let's do that. This is subtraction. Let's change it to cosine of s plus the opposite t. Is that doable? Okay. So now your input values for this formula, this one's going to be obviously your s, because that's what that is, but this one's going to be now negative t. Does that make sense? So I'm gonna write that out. I go cosine of s, cosine of negative t, minus then sine of s, sine of negative t. Cosine s is just cosine s, right? That doesn't change anything. But do you guys know what that is? What cosine of negative t is? Good, that's cosine of t. Remember from the unit circle that if I have, let's just say, let's do 30 degrees here. Cosine of 30 degrees is that thing right there, right? Okay. Well, if I do cosine of cosine of 30 would have been that. Cosine of negative 30, won't that be right there? What's the link between those two values? They're the same, right? And is that going to be the same for all those values? You can't see that one, but they're all the same, right? So cosine of that one, the same as the cosine of that one. Is that doable for everybody? Does that make sense? Okay. So that's why we're just going to rewrite this as cosine t. Okay. Those are even odd relationships that we had mentioned a few days ago. Sine of s, just sine of s. But now I got sine of negative t. Does anybody know what that is? Negative sine of t. Okay. Now I'm going to write it this way because it's these two things are being multiplied together right here, right? So these two things need to multiply together. And again, that reason comes from the unit circle. It's the same logic as what we got right here. If I'm looking at 30 degrees, and this is negative 30 degrees, how do I make those two things equal? I got to multiply one of them by a negative, right? Okay, so sine of a negative 30 is the same thing as the opposite of sine of 30. Sine of negative 30 is negative 1/2. Sine of 30 is a half, but then put that negative in front is how we equate them. Okay, is that doable for everybody? And if you look, you compare all y values of positive angles and negative angles, they should have that relationship that one is positive, one is negative. Okay, so getting back to this, that's why we were able to take this and make it negative sine t. So now, what's a negative sine s times a negative sine t? What's a negative times a negative? Positive. This becomes plus sine s sine t. So now we know that cosine of s minus t is the same thing as cosine t s cosine t equals sine s sine t. Now you can, because you have the commutative properties existing, if you want to write cosine t cosine s plus sine t sine s, that's okay. That's something we can do. I think one of the biggest kind of downfalls of my high school education was that when I was in a science lesson, and I had great science teachers, and I had tremendous math teachers, but the formulas were just provided to me. They weren't told to me. It wasn't explained to me where they came from, that kind of stuff. That there was reason behind them, and I was able to kind of navigate through things, just not very easily. It wasn't until I sat down on my own, and I was in college at this point, and worked through these things, and decided, I'm going to learn where they come from, how to use them, how to manipulate them, that kind of stuff. And learning their derivations, learning that process we went through, and what we went through yesterday, allowed me to eventually apply them and learn them, memorize them, whatever you want to call it, a lot easier. Okay, and to manipulate them and create other formulas and other identities a lot easier. Okay, so hopefully that is kind of a byproduct of going through these with you guys, is their application and their use is then more obvious. A second thing is that I want you guys to not, if you can't go through that process, or the process we went through yesterday, hopefully eventually we get there and you can, but I do want you to know that every time you're given a formula, and I've said this before, but every time you're given a formula in this class, science class, calculus, trig, whatever, there's logic behind it, there's reason behind it, there's a proof behind it, okay? And we can't, as a math or science community, accept it until there is a valid proof behind it, okay? And hopefully you realize that when somebody gives you a formula, they didn't just pull it out of thin air, throw a bunch of numbers and letters together and say it works. There's reason for it, okay? So hopefully we maybe gain that from doing this. All right, so let's talk about where we can use this stuff. We got some examples here. I think we did one yesterday. We did cosine of like 75 degrees. I want to do a different one. I want to do something that we already know. Let's use these formulas and derive something that we already know. I'm going to say cosine of 60. You guys know what cosine of 60 is, right? What is it? That's 1/2 off the unit circle, right? Okay. Let's see if this formula produces the same thing. Okay. Let's use addition. But what are two angles that I can add together to get 60? 30 and 30. Okay. Now the fact that they're the same might not be all that interesting, but it's cosine, so I'm going to go cosine, 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 okay? And I'll explain what I'm saying here in a moment. I always write out kind of the structure of the sines and cosines when I use these rules. And when it's cosine, I know it starts with 3 cosines. Cosine, cosine, cosine. That's kind of like the complementary sign. Does that kind of make sense? Because this was a plus, so this becomes a negative. And then I go sine. Does that make sense? I know in each one of these rules, each one of these formulas of the 6 that I gave you, the 4 that use sine and cosine, or the sums for sine and cosine and differences, we'll use cosine twice, and it will use sine twice. I'm just going to make sure I got them in the right order. Okay. Then I go back, and whatever these orders were, I'm going to plug those in. So, like in this one, it's really not that interesting. They're all 30. We'll see one here in a little bit. They're different, so I can show that pattern a little bit. But this one here is basically that one. This one here is that one, and then we get that one and that one, kind of the same word. Is that all right? Now we evaluate. What is the cosine of 30 degrees? Radical 3 over 2. What's the cosine of 30 degrees again? Radical 3 over 2. Minus, what's the sine of 30? 1/2. Okay. What's radical 3 over 2 times radical 3 over 2? 3/4. What's 1/2 times 1/2? 1/4. What's 3/4 minus 1/4? And isn't that what we already knew? Okay. I like doing those trivial cases because we already knew the answer. So, see if we can replicate that answer maybe a different way, kind of validates this formula. Says this one was going to work. Okay. Now, are there other ways of getting 60 from the unit circle, taking other angles and maybe adding them or subtracting them? What's another way I could have gotten 60? Okay, 90 minus 30. So cosine of 90 minus 30. So now I'm going to go, it's going to be cosine, cosine, cosine as the complementary sign. So this is a minus, so it's going to be a plus. And then I go sine, sine. Then go back and fill in these angles in the order that they are. So it's going to go 90, 30, 90, 30. What's cosine of 90? That's 0, right? Do I care what the cosine of 30 is then? No, because 0 times whatever that is going to give me 0, right? Put a number here. Plus, then what's the sine of 90? 1. What's the sine of 30? 1/2. I get 0 plus 1/2, which is just 1/2 again, right? So do you see that we arrived at cosine of 60 using two different kind of approaches? One by adding angles together, one by subtracting them. Okay. You can do it the same way. Let's say I can get 60 by taking 120 minus 60, or maybe I can go 180 minus 120, right? That gives me 60 as well. So if you note all your angles around the unit circle, it doesn't matter which ones you subtract or add together, as long as that sum or difference gives you 60. Okay. I like to use the smaller ones if possible. So for instance, if they ask me what is the cosine of 15 degrees, I'm going to try to use 45 and 30. I don't want to use I don't know, 135 and 120. Does that make sense? Okay. They still subtract getting 15, but 45 and 30 are a little bit easier to deal with. So let's see kind of that type of question. And it's going to maybe start off looking a little bit different. I'm going to ask you, can you find the cosine of pi over 12? Cosine of pi over 12. Cosine of pi over 12. Now here's the pain in the butt about pi over 12. Okay. We don't have it memorized from the unit circle. Okay. So we probably want to use the sum or difference of some other angles that we know off the unit circle. If I leave it in radians, I have to know that pi over 4 minus pi over 3, or sorry, pi over 6, is equal to pi over 12. Because this ends up being 3 pi over 12, and this is 2 pi over 12, and that gives me pi over 12, right? So I have to know that cosine of pi over 12 is actually pi over 4 minus pi over 6. That's kind of a pain in the butt, okay? I would much rather, and I think you would too, do this. And you probably wouldn't write it down this way, but if I write that, what's that going to do? Change it into degrees. And it changes it into 15 degrees. Is that easier to see than the cosine of 15 degrees is the same as cosine of 45 minus 30? And now do the problem with that. Okay? So every time they ask me something like this, that's kind of what I'm going to think about. We know, and this could be an alternative approach, we know that pi over 6 equates to 30 degrees. Okay? So every multiple of pi over 6 is on the unit circle. We've dealt with that a lot. Well, pi over 12 would be how many degrees? Yeah, it'd be half of this. Pi over 12 is half of pi over 6, so it's half of 30. So every time you see a 12th as a denominator, you know that it's a multiple of 15 degrees. Okay? But now if I write it that way, if I write it as cosine 45 minus 30, cosine of 45 minus 30, we're going to go through and write cosine 45, cosine 30, cosine, okay, that's a minus, so that's going to be a plus, and then sine of 45, sine of 30. What is the cosine of 45? Right, 2, 2. What's cosine of 30? Radical 3 over 2. Sine of 45? Radical 2 over 2. Sine of 30? 1/2. So I get radical 6 over 4 plus radical 2 over 4. And that's a very similar answer. If you go back and look at the video from yesterday, we did the cosine and the sine of 75. Got a similar answer. And I want to take a moment to open up the unit circle and talk about why that's a similar answer. If we look at the unit circle, 15 degrees would be like that point right there, right? Okay. We just determined the cosine was radical 6 plus radical 2 over 4. Eventually, maybe we would find the sine as well. And I'm thinking the sine is probably maybe radical 6 minus radical 2 over 4. I'm not sure. Don't quote me on that. But that's the cosine. Okay. Well, think about what happens then with every other point on the unit circle. Isn't this point right here going to have the same x value? And wouldn't this be 15 degrees? So at 165 degrees, we now know the cosine of 165 because of this angle over here, this reference angle from the first quadrant. Okay? Can I look at that angle, okay, which would be now what, 345? Is 345 going to have the same cosine value? Okay, now this one would have been negative, I guess, right? So I should say negative radical 6 plus radical 2 over 4. And a lot of times you actually see that negative being distributed through, so it's negative radical 6 minus radical 2 over 4. But it is still in relationship to that one. Is this one going to be the same x value as that one? Okay. Now, think about what we did with 30 and 60. 30 and 60 were a reflection of one another across that line. It's terrible, but it's the line y equals x. Okay? And everything that's a reflection across the line y equals x is You're going to have that inverse relationship, right? Where the A's and, or the X's and Y's flip-flop, or the A's and B's flip-flop. So that's how these two kind of relate to one another. Well, isn't there an angle right here of 75? That is going to flip-flop with that one right there, 15. Okay? So when I come up here and I ask what is the sine of 75, it's going to be the same thing as the cosine of 15. It's going to be radical 6 plus radical 2 over 4. So if you go back to yesterday's stuff, yesterday's video, when I asked you, well, I guess we walked through this one, I think, but we also at the same time did the sine. The sine of 75 is going to be the exact same thing as the cosine of 15. Okay. And what we're doing there, guys, if we look at, I said cosine of pi over 12 was what we started with. Is just that number right there, right? Okay. Now if I do square root of 6 plus square root of 2, all divided by 4, does it give me the same number? So we just found the exact value for that on the unit circle. When we look at the unit circle, then that tells us that not only do we know the traditional 17 points that were multiples of 30 or multiples of 45, we now have 8 additional points that are multiples of 15. They go all the way around here. So now we could potentially be asked about 25 different points on the unit circle and know their exact values. Okay. Now, I'm never going to ask you to memorize the ordered pair for cosine, the ordered pair for 15 degrees or 75 degrees or anything like that, because if you do need them, you now have formulas that create them, right? They just don't show up enough for us to really want to memorize them or need to memorize them, okay? Like we did with the unit circle with the other points. Hopefully you're seeing that though it's been maybe 4 or 5 days since we've directly used the ordered pairs off the unit circle, they come back and we need them, right? Okay, and that's going to be kind of the pattern as we move on through the year. We might go 2 or 3 days without asking the question, what's the cosine of pi over 6? But then in the next class period, we might use that the entire class period. Does that make sense? So it's something you can't forget. Not every day do we multiply, but you haven't forgotten how to multiply since like the 3rd grade, right? Okay, so same logic. Okay, not every day are you going to use the sine and cosine from the unit circle, but you do need it. Okay, so let's go through and a couple other questions here to talk about. This is just kind of the reverse format of one of these formulas. Because it starts with cosine, that tells us that this is the same thing as cosine of 2 things either added or subtracted. But if I look at that sign right there, what's it tell me that they're being done, or what they're doing with one another inside here? Adding together, okay? And what are those 2 things that we're adding together? 14 and 46. What is 14 plus 46? 60. And what is cosine of 60? 1/2, right? So that's kind of what they're asking you to do there in that question. Says use an addition or subtraction formula to write the expression as a trigonometric function of one number. Cosine of 60 would be that trigonometric expression of one number, but we can evaluate that even further down to 1/2. Again, with these, I mean, you can type this in, cosine of 14 times cosine of 46 minus then sine of 14, sine of 46. What did I do? Ah, degrees. You 0.5, right? Okay. That's the one thing you got to make sure if you're using your calculator. Still going to go back and think about what units are you using, degrees or radians. So we just said that is equal to then cosine of 14 plus 46, right? Does that make sense? Can I write it this way? Cosine of 46 plus 14. Addition is commutative, right? Okay, so it's not a problem. Is subtraction commutative? In general, it's not. But what do we see there? They're the same, right? Why? Yeah, if I'm looking at my unit circle, and that's theta, and that's negative theta, that direction's negative theta, that's positive theta, isn't that x value right there the exact same thing as that x value right there? So this would be cosine of what, negative 32? Or even odd identities tell us that's the exact same thing as cosine 32. Can I do the same thing with the sine? If I say, let's say I said sine of 14 plus 46 gives me that, which that's radical 3 over 2. Is that the same thing as sine of 46 plus 14? Addition is always commutative, right? But what if I do this? If I go minus 46, so that's sine of negative 32, right? And this would be the sine of positive 32. Are those the same? No, because of the even odd idea that this one is below the x-axis, so the y value is negative. This angle is above the x-axis, so the y value is positive. Okay. So those are just little kind of intricacies with these formulas that you can either learn and use, or I would think that you would be safe by not even by neglecting them and just kind of following the structure of that is set up in the problem for you. Okay, so let's do. Yeah, we got plenty of time. All right. This one here, I want to talk about this one because this one's going to generate for us the other formulas for addition and subtraction that we haven't talked about. We have proven the cosine s plus t and the cosine of s minus t, but we have not proven the sine of s plus t and the sine of s minus t. Okay, so we'll try to do that here after we show this. All right, so let's prove the cofunction any cosine pi over 2 minus u is equal to sine u. Okay. Well, this is a difference, right? It's a difference of two angles. So I'm going to rewrite cosine of pi over 2 minus u as it's cosine, so it's cosine, 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 sine, sine. I'm going to go back through and put in my angles pi over 2, u, pi over 2, u. All right, what's cosine of pi over 2? 0, right? And then we've got times cosine u. Plus now, what's the sine of pi over 2? 1 times the sine of u. What's 0 times cosine u? 0. 1 times sine u? Sine u. And that is equal to the right-hand side. Okay. So we do see that that is a true identity. And that's what, if you remember back to the co-function identities, we've said these or stated these before, but we only proved them graphically. We showed you ultimately that if I type in sine u on the graph, it gives me my sine curve. And if I type in cosine of pi over 2 minus u, it essentially shifts it left or right, pi over 2 units, and matches up with the sine function, right? Okay. But now here is the algebraic proof of that. Okay. That being said, let's use this to come up with the proof of sine of s plus t. Okay, so we're going to prove that, and I'm going to give myself a little bit more room, I think. Yeah, that's better. We just said that the sine of u is the same thing as the cosine of pi over 2 minus u, correct? That's exactly what we just wrote down. Okay. So I want to replace my u. Okay. I want my u to actually be s plus t. It's going to do that a couple more times. All right, so try to color code things there for you. We see that the u is being replaced with s plus t. So then on the right-hand side, I replace that u with that sum of s plus t, right? Okay. Now don't write down what I'm about to write, because it doesn't gain you anything. But if I just left it this way, this is going to be cosine of pi over 2 times cosine of s plus t plus then sine of pi over 2 sine of s plus t. And going through here, we know cosine of pi over 2 is 0. So this thing's going to wipe away. We know sine of pi over 2 is 1. So I got 1 times sine of s plus t, and I'm just left with sine of s plus t. So it does show us that, yes, indeed, we do have the right information here. This does equate, okay? However, it doesn't generate anything new for us, right? Let's see if we can work through here to see if we can generate something new. And the idea stems from us being able to realize that it is perfectly fine to do this. And distribute that negative through the s plus t, right? Now, we have, if I had like 2 minus 3 minus 4, maybe I don't want to write this way. Let's just kind of, we can use the associative property. We can use the associative property and group those two. Do that subtraction first. Does that make sense? Okay. So now we see that we have our first angle. Okay, so this is one angle, and this is a second angle. So those are our components for the cosine. So the cosine is going to look something like this. It's going to be cosine of something times cosine of something. This is subtraction here, so this is going to turn into addition. Sine of the first angle, sine of the second angle. Now the first angle is pi over 2 minus s. The second angle is t. Pi over 2 minus s, and then t. This thing here, cosine of pi over 2 minus s, and there's a couple different ways you can kind of really do this. Haven't we said that cosine of pi over 2 minus u, and it doesn't really matter what our u is, so here our u is at s, but cosine of pi over 2 minus s, isn't that going to be the same thing as sine of s? Does that make sense? Okay. Or if you're more comfortable doing it this way and saying this thing here is going to change to cosine of pi over 2 cosine of s plus sine of pi over 2 sine of s, that's fine. So that set of brackets is what I've got in this brace here. But then I still got that cosine of t on the outside. So that cosine of t. Now going through this, what is cosine of pi over 2? 0. So those two things wipe away, right? What's the sine of pi over 2? 1. So I've really got 1 times sine of s in here, right? So I realize you got sine, this thing here all turns into just sine of s, right? So I have sine of s times cosine of t as everything up to kind of that point. Now I still got this stuff over here, okay? And we can kind of evaluate this, extend this, and say that this is sine of pi over 2 cosine of s minus cosine of pi over 2 sine of s, and then times sine of t, and do the same kind of simplification. What's sine of pi over 2? 1 times cosine s, right? So this is just, I'm going to wipe that away. So we got cosine s left over. What's cosine of pi over 2? 0. So that's going to wipe away completely, right? And all I'm left with is that then times that, right? So we got cosine s times sine t. And what is that? We now have that identity, or that formula. Does that make sense? Okay. Now, whether we're I'm not on a test for quizzes. I'm not going to ask you to ever repeat them. Okay. But it's visual. It's going through the word. It's using identities and these formulas to recognize and to show that there is reason behind all these what look to be complicated formulas, but they're really nice, convenient formulas for us to deal with instead of dealing with all that garbage inside. Does that make sense? So in respect to what they could be, even though they look complex, they could be a lot more complex. Okay. All right, so where do these things help us? Elsewhere, just go through a couple examples, and we're not going to get through all of these today. Where'd it go? All right. I want to do this one. And if you remember, a couple weeks ago, man, why does I keep doing that? A couple weeks ago, we did a problem like this in Chapter 5, and I made the comment that it's going to come back. It's going to be a very similar question. We'll add to it a little bit, but this is an approach. This is a type of problem that we've already seen. The first thing it says is evaluate this. This is what the question is. Can you evaluate that? Okay. Can we find out what cosine of theta minus phi is? Okay. And it doesn't matter what these symbols are. You want to use A and B, X and Y. It doesn't matter. The only way that we can evaluate that difference there is to rewrite it as cosine of theta minus phi. Using our addition and subtraction rules, we just said that is cosine of theta times cosine of phi plus sine of theta sine of phi, right? Now, looking at the rest of the problem, we need to evaluate this thing. So we need to be able to plug in what is cosine of theta. Do we know cosine of theta? It's 8/17, right? Now here's the issue in this question. Do I know cosine of phi? Up here, does it tell me what cosine of phi is? Does it tell me what sine of theta is up here? Does it tell me what sine of phi is up here? No. Okay. However, it implies them. It kind of tells me. Okay. We're going to draw a picture here. If you know theta's in quadrant 4, doesn't that mean theta kind of looks like that angle there maybe? And does that create a right triangle there? So if that's theta, we know that if we can learn anything about that angle right there, it's the same as for theta, right? Remember doing this type of question? If I know the cosine of theta is 8/17, cosine is adjacent over hypotenuse, right? Do you now know what this distance here is or have the ability to find that distance? Pythagorean theorem says it's -15. Okay. So now, with that triangle, it's for theta, so it's really only going to give me that. But now do you know what the sine of theta is? Opposite of hypotenuse, right? It's -15 over 17. Still got a problem because I don't know anything about phi right now. I don't know what those substitutions are going to be. But I've got information here that's going to allow me to do it. Phi is in quadrant 2. So that's going to provide us that right triangle, correct? The tangent, so I'm basically going to be learning everything about that angle right there. The tangent is -√15. So tangent is opposite over adjacent, right? So make it right that way. Opposite, that's my adjacent, so 1 is my adjacent. Now, which one of those actually carries the negative sign? That's the 1. Pythagorean theorem is going to tell you your hypotenuse eventually is 4. Square that, I get 15. Square that, I get 1, right? And together, I get 16. Square root of 16 is 4. Now, do you know the cosine of this angle? Cosine of phi? It's adjacent divided by hypotenuse, right? You know the sine of that angle? Opposite over hypotenuse. So now I get -8 over 68 plus -15 root 15 over 68. And if you can write it that way, you can leave it that way if you want to. I'm just going to go ahead and write this as -8 minus 15 root 15 over 68. But for this particular problem, that is our exact value for cosine of theta minus phi. So what that tells us, guys, is if we were to go through, take our calculator, because you can check it with your calculator. Essentially, what you would have to do is take maybe tomorrow we'll talk about how we can calculate. We're around time here. What we would want to basically take is figure out what theta and phi are using kind of your sine and cosine inverses, and you can find what those measurements are, and you can obviously subtract those in, correct? Makes sense? So go down here, use like our sine, our cosine, find those measurements. You evaluate that in your calculator, then you evaluate this in your calculator. Yeah. All right, so when class wrapped up, I said you could be able to check yourself here. If you're going to check yourself, what you need to do is find out exactly what this theta angle is and what this phi angle over here was. And the way we do that is you use our inverse function. So I can say that cosine inverse of, let's just deal with theta first. Um, Cosine inverse of 8/17. Okay, so 8/17 gives me 61.92. Now 61.92 would be as if this angle was in the first quadrant. We know it's in the fourth quadrant, so I actually got to take that and remove it from 360. So let's see if we can do that here. So that angle right there, 298, is this theta right here. Okay. Now I'm going to do the same thing over here and try to figure out this one. I'm just going to use the tangent that they gave us. They said that tangent was negative root 15. So I'll say arc tangent of negative square root 15. That gives me that angle, which is a fourth quadrant angle. Okay, but we know that this thing's in the second quadrant, and what happens essentially here is that what I've just been provided. Give me 1 second, my tablet died. All right, so the negative 75 degrees that Desmos just gave was that angle there. So this angle here is also about 75. Okay, so how do I find phi then? How do I find that phi? Okay, I'm going to take 180 minus 75. So 180. Now I'm going to write plus, but then I'm going to copy this negative number, so that's still subtraction. And it gives me 104.477. So now I have, this here, this was phi, and this here was theta. So I'm going to go cosine of this number, Control C, V minus phi, which would have been this number. And I get 0.9718198. Okay, so now we're going to see, is that identical? Is that oh, come on. Try to get everything here so you can see it. Is that we'll get there. All right, is that identical to this thing here? So I'll type that in. Negative 8 minus 15 square root 15. Put all that in parentheses, divide by 68. And we do see that these two numbers, that one there and that one there, are identical. Okay, so it's kind of a way to check yourself. Now, is it a really nice, convenient way? No, you got to do some work, but I'd rather do the work and know that I'm right than potentially made an error somewhere. So every one of these, you have that ability. Yeah, you just gotta, the more you understand about your relationships between cosine and arc cosine and all your identities and stuff like that, it's going to be easier for you to have alternative routes to check your work.